Hi everyone. For those of you who don't know me, my name's Mr. Harris. I'm going to be helping out Miss Gum, who's obviously got you guys for the next few weeks while Miss Warrior's out. I'm unfortunately in isolation with COVID at the moment, so this week you'll get a few videos from me helping you through some of the ideas of the course. And then hopefully from next week I will be back at the school and able to be in class a little bit with you guys to help you guys out with some of the chemistry content you're going to be doing over the next few weeks. So today, I'm going to run you through some of the concepts of ionic bonding. Now, I believe you guys are familiar from last term with the idea of ions. I will go over them again, and basic stuff like your periodic table and how that gives you information about the atoms. You should have that information available to yourselves. Obviously, if you do need help with some of those basic ideas, you can ask Miss Gum or even send me an email or direct message at different points in time, or once I'm back next week, you can certainly ask me face to face. But I'm going to go as though you kind of know what those ideas are. I will go through a couple of examples so you'll get that reminder as we work, but that's what we'll be looking at today. So ionic bonding is what we're looking for. So we're just going to start with a very quick recap of chemical formula. Once my computer catches up, there we go. So chemical formula, as we know, tells us how many atoms and what type of atoms there are in a particular compound. One that you'd be very, very familiar with at this point, H2O. So 2 hydrogens, 1 oxygen. H2SO4, 2 hydrogen, 1 sulfur, 4 oxygen. You can obviously have some very complicated ones of these, but for the most part, they're going to be relatively simple, like these two you can see in front of you. When we have ionic compounds, these are the types of compounds that are formed between metal atoms and non-metal atoms. So, if we're naming an ionic compound, we'd name the metal atom first, and then the second part of that would be the non-metal, and we change the end to "-ide". So here's an example. Magnesium oxide is 1 magnesium atom, 1 oxygen atom. So the magnesium is written first and is named first, doesn't change its name, and then the oxygen at the end there becomes oxide. Another common one that you would see, sodium chloride, so 1 sodium atom, 1 chlorine atom. And then here we have iron bromide. Now there are 2 bromine atoms here, but we don't have to worry about that in the name. We just name the type of atom it is, so iron, bromide, no mention of the 2 in the name at all. So as quickly mentioned, the ionic bond, this is a metal atom combined with a non-metal atom. Excuse me. And how these work is our metal atoms lose an electron and they become a positive ion, which, like I say, I believe you've seen this previously. And the non-metal atoms actually gain an electron and become a negative ion. So the positive ions we call cations, and the negatives we call anions. And an ion, just in general, is any atom that has a charge. So it's an atom that's either gained or lost an electron. So in terms of an ionic bond example, so let's look at sodium and oxygen here. So sodium has 11 electrons, it loses 1. We'll go through that in a little bit more detail in a moment. So once it's lost its 1 electron, it becomes an Na plus ion. The oxygen atom has 8 electrons, it gains 2 to become a O2 minus. Now this all happens because they want that 8 electrons in their outside shell. So depending on how many electrons they have in their outer shell normally will determine whether or not they want to gain electrons or lose electrons. So if you've got this happening with metals and non-metals, the metal atoms lose the electrons, the non-metal atoms gain those electrons that have been lost. So the metal atoms let them go, the non-metals pick them up. And then that creates what we call the ionic bond. So the positive metal cations and the negative non-metal anions, they attracted together by positive and negative charges. Opposite charges attract, and then they want to stick together. So here's an example, lithium and fluorine. So this is a pretty simple one. So I'll give you these diagrams to start with. These are our electron dot diagrams. I'm sure you've seen these. So we have lithium on the right there with 3 electrons, and fluorine on the left with the 9 that you can see there. So fluorine, if you look at your periodic tables, you'll see that fluorine has an atomic number of 9, which is where we get those 9 electrons from. Now this term valency, you've probably heard this, but if you haven't, valency just refers to the number of electrons that are in the outside shell. So if we look at fluorine there, we can see there's 2 shells, 2 electrons in the inner shell, and 1, 2, 3, 4, 5, 6, 7 electrons in the outer shell. So that means it's a valency of 7. All atoms want to have 8 electrons. All atoms want to do the least number of things to get those 8 electrons. So in the case of fluorine, to have a full outer shell, you could either lose all of those electrons to just leave the 2 in the middle, lose 7 electrons, or it's much easier to actually gain 1. So if it can gain 1, find 1 extra electron, then it can add that to its shell and end up with an extra electron, which makes it a little bit more negative than it should be. So it becomes an F- ion, or a fluoride ion. Lithium essentially does the opposite. Now lithium has an atomic number of 3 electrons there. It has a valency of 1, because there's 1 electron in the outside shell. It's going to lose that 1 electron, and it becomes an Li plus ion, because now it has more protons in its nucleus than it has electrons in the outside shell. Electrons in any of its shells, sorry. So once that's happened, so just going back, you can see the 2 atoms there. Once they become their ions, the electrons actually shift. So now fluorine has 8 in its outside shell, and it is negative overall. Lithium has 2. It's lost that outside shell, and so it's positive overall. So now we have a positive and a negative charge. They attract to each other. They stick together because of that charge by what is called electrostatic attraction. This is what we call an ionic bond. So I'm going to go through a couple of examples here. So how do these things add up? This is a slightly different example. You saw with lithium and fluorine there was just 1 of each of those atoms. If we have calcium and chlorine, these actually bond together and form a compound, calcium chloride, which is CaCl2, which, remembering what our formula tell us, calcium and 2 chlorines. So calcium forms a 2+ ion, and I'll go through that in a moment. And Cl- is our chlorine ion, so you need to have 2 chlorines for every calcium to make those numbers add up. And I will show you how and why that works. So we start with calcium. Looking at your periodic table, you'll see it has an atomic number of 20. So I'm going to go and fill in those electrons there on an electron dot diagram. 2 in the middle, 2 layers of 8, and then 2 on the outside, which gives us a valency of 2 in that outer shell. Because that number is pretty small, it's going to be easier to lose those electrons, so calcium will lose both of those and form a Ca2+ ion. Chlorine, atomic number of 17. 17 electrons there. That's a valency of 7. 7 electrons in the outside shell. Same with fluorine that we saw previously. It's going to try and gain 1, which will make it a Cl- ion. So as we saw with fluorine and lithium, excuse me, fluorine and lithium, we saw that fluorine picked up the electron that lithium dropped. Same thing happens here. Chlorine picks up the electron that calcium dropped. However, calcium is dropping 2 of those electrons. So we actually need 2 chlorines to pick it up. So calcium loses 2, and each chlorine gains 1, which is why we have a formula of CaCl2. Still just called calcium chloride though. Alright, time for a bit of practice for you guys. Pause the video and have a go at these following diagrams. So sodium and chlorine, which I will go through an example in a moment. Then magnesium and oxygen, beryllium and oxygen. So pause now, have a go, and then come back and I'll show you the solution for sodium and chlorine. Okay guys, hopefully you had a good go at that. If we look at sodium and chlorine here, so we'll go through that same process I showed you with the previous example. Sodium, an atomic number of 11. So if I add those electrons to the dot diagram above, there's 2 in the center. Then we have a layer of 8 that adds up to 10, which means we've got 1 extra left over in the outside shell. So that is a valency of 1. A valency of 1 means we're going to lose that 1, and it's going to create a Na plus ion. Now chlorine, I'm going to work this a slightly different way. We've seen chlorine done previously on the other slide, so let's just have a look at it a little different way. If you look at your periodic tables, chlorine is in group 7 or 17, depending on how you've labeled it. But that group will tell you how many electrons there are in the outside shell. So if it's in group 7, 17, that means it has 7 electrons in the outside shell, or a valency of 7. The atomic number is 17, which means we need 17 in total. So I've got 7 there. I add 2, that's 9. And then I add my full shell of 8 in the middle, giving me a total of 17. That's another way you can get these dot diagrams drawn pretty quickly, rather than counting your way out from the inside. Start at the outside and fill in everything underneath. Alright, so we've got a valency of 7, which means it wants to gain the 1, becomes a Cl- ion. So if we have these two here, we can see that now sodium's going to lose that electron, chlorine's going to gain it. Sodium becomes positive, chlorine becomes negative, they stick together and they form a compound called sodium chloride. You've got the examples here for magnesium and oxygen, you can work through those yourself, and beryllium and oxygen as well. So if you got stuck with those previously, hopefully the solutions to sodium chloride helped you out. Now, doing those dot diagrams is one way you can get this formula. They do take a fair bit of time though, drawing out all the diagrams, working out where those electrons are going to go and where they're going to move, etc. So instead of doing that, this is another way you can work out what your formulas would actually be. So work out what the atoms are and what ions they're going to create. So I've got a couple of examples here: magnesium 2+, oxygen 2-, and sodium and chlorine, like we just saw in the previous example. Now, if those numbers are the same, so magnesium is 2+, oxygen's 2-, sodium is 1+, chlorine's 1-, then the charges balance out, they all cancel, everything adds up nicely, they're all neutral, and so you can basically put those two atoms together, and that gives you the formula for the resultant compounds. So magnesium oxide and sodium chloride here. Now, if your ions are not the same, so let's look at this example. This is the one we saw previously, magnesium chloride. We saw calcium chloride, but same groups here. So magnesium is a 2+ and chlorine is a 1-. We can do this process called crossing over the charges, or you also hear it called swap and drop. So what we do is we take these numbers, the magnesium, the 2 there, the chlorine, the 1, and we swap them over, and they go onto the other piece. So if we remember our calcium chloride, calcium was a Ca2+, Cl1- for the chlorine, and then that became CaCl2, because we needed 2 of the chlorines to cancel out that calcium. Here we have the same thing, Mg2+ tells us that there must be 2 chlorines, Cl1- tells us that there must be 1 magnesium. When we write it in the formula, we don't need to include the number 1, so we'll leave that out. Magnesium chloride is just written as MgCl2. Now, if you've got different numbers, the process works exactly the same. Here we have Al3+, so that's an aluminium ion, and O2-, an oxide ion. We swap and drop. So the 2 there tells me that I'm going to need 2 aluminiums. The 3 on the aluminium tells me I will need 2 oxygens. 3 oxygens, my apologies. So we end up with a formula of Al2O3. So swap the numbers over, they drop down the bottom so they're part of the formula. We write them up the top for an ion, down the bottom for a formula. The charges disappear, and there is my finished product. The next few slides have a couple of practices for you. You can have a go at some of those. Once you work out your ions, it should be a pretty easy process. So there's a few opportunities for practice there. When you do look at some of the formula for different compounds, you'll see that some of these actually contain pieces that have more than one atom. So all the examples we've seen so far have been one type of metal and one type of non-metal. So sometimes you'll see these larger pieces, OH, NO3, SO4, etc. These all have special names, and these all attach to one of the metals, or in the case of ammonium, replaces the metal in the formula. So you basically treat them the same, you do the same things with them, but you just use it as a whole piece. So we have a look at a couple of, before I go on, I believe the PowerPoint you have access to in Teams, in Sector, says you need to memorize these. You don't actually need to memorize all of these ions completely. It's good practice, so it's a good idea, makes everything a bit easier and a bit quicker for you, but you would be provided with the lists of these in a test or an exam at Year 10, but if you are planning on going through into Year 11 chemistry, then remembering these would become important. And it's a good idea for everybody to give it a try, because you may need it for an in-class activity. Yes, so looking at the formula and the way we would use these, like I say, we treat them basically the same as we would for any other compound. So start with the two ions there, so Mg2+, so the same magnesium ion we've seen previously, and the OH1-, that was a hydroxide ion seen on the previous slide. We swap and drop, and so we end up with 1 magnesium and 2 hydroxides, so we end up with this. Now, just like in math, we use the brackets to show that there is 2 of everything inside the brackets. So our hydroxide ion is an OH piece. It comes as a whole chunk, so we treat it as a whole piece. Mg, brackets, OH, close the bracket, and then the 2, because we have 2 of the OHs. So we look at a different example, a more complicated looking one. Ca2+, PO4 3-, so calcium and phosphate here. Swap and drop, and we end up with Ca3, PO4 in brackets, and then 2 of those. So Ca3, PO4, 2. So it's certainly more complicated looking. Visually, yes, it looks a lot more complex than what we did previously, but it's exactly the same process. And if you just keep those pieces as a chunk, PO4, OH, CO2, NO3, etc., they all work exactly the same. Opportunity for you to do a little bit of practice. So you can pause here, have a go at a few of those. There's also a quick quiz for you to have a look at. See if you can remember some of these things off the top of your head. Final thing before I finish up this video is just a very quick note on what you sort of get when you have these ionic compounds, what kind of materials they produce. So where you have positive metals and negative non-metals, they often arrange themselves into a lattice or a crystal. So they can make these large repeating structures with lots of positive ions stuck together really strongly with the negatives next to them. And with all of that positive and negative together, makes it really hard to break these structures. They're really high melting points, really strong chemical structures. So this is just a bit of a close-up view of this one. This is sodium chloride. These kind of compounds form crystals. so salt crystals in this case. Okay, everyone, thank you for your attention. I know this was a bit of a longer video here, but a couple of things to pause and go back and have a look at. And as I say, I will be making a few more of these over the next few days for you to have a look through, but then we'll be hopefully back in class or back on site for you guys to give you a bit of help over the next couple of weeks. All right, thanks everyone. Bye.